Good morning, students. I hope all of you are fine and are doing well with your studies. I welcome you all to this online classes in physics for standard 12th. Last class we devoted some time discussing the magnetic field due to current carrying straight conductor circular wire. We'll proceed further today to discuss the magnetic field pattern, the value due to a solenoid and a toroid. To begin with, let me revise again the pattern of magnetic field length due to a circular coil. Suppose there is a wire which has been wrapped in the form of a circle. It may have 1, 2, 3, 4, 5 turns, not more. So that we treat it as a circular coil and it carries some current. The direction of current when viewed from this side of the coil is that side, I am standing this side. From this side, the direction of current is anti-clockwise. If it is anti-clockwise at the top, it will come out of the plane of board, and at the bottom of the coil, it enters into the plane of board. यहाँ करंट बाहर की ओर आ रही है और यहाँ पर करंट अंदर की ओर जा रही है. So that you have to understand. And the plane of the coil का plane ऐसा है. Plane of coil is perpendicular to the plane of board. Then the magnetic field lines, which I have represented by these curves, what are the observations? First, near the center, the magnetic field lines are almost parallel to the axis. If we change the direction of current का direction यदि change करते हैं, then the direction of this magnetic field will also reverse. ये उल्टा हो जाएगा. But they are almost parallel to the axis. Observation number 1. So, first observation, near center के पास, the magnetic field vectors, they are parallel to the axis of the coil. And as you move away from the center, जैसे center से हम लोग दूर चलते हैं, the magnetic field lines get more and more curved. You can see here magnetic field lines are almost like a circle at the periphery. So this you can guess. Here the current is coming out. If current is coming out, and hold the conductor in your right palm with the thumb pointing in the direction of current, then fingers will curl like this. Fingers will curl like this. That's why this is the direction of magnetic field. ठीक उसका उल्टा यहाँ पर होगा. Now this we have discussed earlier. Now instead of suppose one turn, एक coil के बजाय, suppose I have one more coil which is placed just adjacent to it. Here the current was coming out, here also the current will be coming out. So I'll represent it by dot, and here I'll represent it by cross. These dot and cross, they represent the direction of current. ये current के लिए मैंने represent किया है dot and cross. And there is one more term. यहाँ पर coil है, मान लीजिए. So this solid part is out of the board, and this dashed part is on the other side of the board, inside the board. Okay. So it will also have a similar pattern. इसका pattern भी exactly similar रहेगा. And the combined magnetic field pattern at the center, near the center, we assume they have a common axis. So the net magnetic field will just add up. So they will almost be straight line near the center. Center में almost straight lines ही रहेंगे. But as you move away, its magnetic field line will also be like so. ये कुछ इस प्रकार का रहेगा. Now these two will combine. The figure might look a bit exaggerated, but it will be like so. This is the magnetic field line due to both of the coils. Here also the pattern will change. Now suppose I have one more, then one more, then one more. Likewise, if you go on adding more and more terms, This is the third coil. Then near the center, the Matic field lines will almost be straight lines now. And here at the near the edges, they will form complicated curves like so. इस तरह का पैटर्न एक आएगा एंड आउटसाइड दे विल बी there will be pattern like this. A very complicated pattern will be there if we have only 3 turns or 4 turns. But if we make these turns closer, एक दूसरे के पास लेते जाएंगे, and if we increase the number of turns, then these deviations will almost minimize. Clear? So let's try to draw that figure. And in that case, when we have a number of turns placed close to each other, the figure that we get will be something like this. Wire wrapped again and again and again over some cylindrical surface, it will form what we call as a solenoid. So क्या कहेंगे हम लोग? Solenoid. So today our topic of discussion will be chiefly solenoid. So before we discuss the values for magnetic field due to a solenoid at points inside and outside it, let us complete this particular pattern. So if we have a solenoid, I'm drawing one more figure. At the top, current suppose leaves the board, comes out of the board, and at the bottom, current will enter into the board. So at top, I'll put dots. These dots are for currents. And at the bottom, I will have crosses. So these dots and cross, let me remind you again, they are for currents. ये current के लिए है. That means current is coming out of the board, current is entering into the board. This is the first turn. Then second turn, then third turn. एक ही तार को लपेटा हुआ है. Many number of turns are there. As discussed earlier, along the axis, near the center of this, the magnetic field lines will be almost parallel to each other, lying parallel to the axis. ये इस तरह से रहेगा. The closer the turns are, the more and more parallel they will become to the axis. इसको जितना दूर रखेंगे उतना ज्यादा डेविएशन रहेगा. किनारे जाने पर ये कर्व्ड हो जाएंगे. That is the thing. For the sake of clarity, I have drawn it so very far, but if you make them very close, these field lines will become almost uniform. ये कैसे हो जाएंगे? Uniform, and they will be parallel to the axis. Now this pattern, if you see here, current is coming out, so fingers will curl like this. The pattern of magnetic field lines will be like so. इसका भी कैसा होगा? ऐसा होगा. Just try to understand. In between the turns, if you see, due to this one, the magnetic field is in upward direction, and due to the right turn, the magnetic field is pointing in downward direction at these points. So they tend to cancel each other like this between the turns. So in between the turns, the magnetic field will be very, very negligibly small. Here also. So between the turns, the magnetic field approaches how much? 0. Because the two adjacent turns will have a magnetic field in opposite directions. Near the center, I have discussed, they will be almost parallel. Why I say almost? Because they will become exactly parallel near the center of a solenoid, which is very, very long, infinitely long. If it is infinitely long near the center, at the middle of the solenoid, we can say that the magnetic field lines are exactly parallel. But for a solenoid like this, it is certainly not of infinite length. So for finite length solenoids, as you move away from the center towards the edge of the solenoid के end तक जाएंगे तो magnetic field lines curve होने शुरू हो जाएंगे. Instead of like this, they will start curving like so. And it will be forming a loop. एक loop form करेगा इस तरह से. outside, just outside the solenoid, magnetic field will be opposite in direction to the magnetic field inside the solenoid. As you can see here, inside the solenoid, magnetic field lines are like this. Outside the solenoid, you can see these two will add up. But one difference will be there. Magnetic field inside the solenoid, solenoid के अंदर जो magnetic field रहेगी, that will be quite strong. सारे के कारण वो components add up होंगे. But magnetic field outside the solenoid, it will be in opposite direction, no doubt, but it will be weak. And the direction will be opposite to B in. B out और B in के directions जो है opposite रहेंगे. These are the things for a tightly wrapped solenoid which has a finite length. जैसे हम लोग solenoid को long कर देंगे, for long solenoid क्या क्या चीज हम लोग assumptions करेंगे? Number one, magnetic field inside the solenoid B in will become uniform. Very important. If you pack them tightly and you make it very long, then the magnetic field inside the solenoid will become uniform and will be parallel to the axis. Point number one. Magnetic field between the turns तो जीरो था ही. Outside the solenoid, B out, जो कि पहले weak हुआ करता था, if you have a very long solenoid and the turns are very closely spaced, एकदम नजदीक है, then for a solenoid somewhere in the middle here, outside the solenoid, the magnetic field B out tends to zero. Tends to zero. So it will be exactly equal to zero for an infinitely long solenoid for points outside the solenoid. So these 2 points you have to remember, students. Inside the solenoid, magnetic field will be strong. I should write strong also. And it will be uniform, directed parallel to the axis. Outside, it will be weak for finite solenoids, and it might tend to zero, very, very less, for cases where we have infinitely long solenoid or very long solenoid, where the turns are very, very, very closely packed. So these two properties we will use in deriving the expression for magnetic field due to a long solenoid, like so. So let us discuss the derivation. We will use Ampere's circuital law for the derivation. But note that this derivation which I am going to discuss is valid only for long solenoids. Okay. Let's see. So while applying the Ampere's law, we have to choose an Amperian loop. तो पहले मैं solenoid बना देता हूँ. So these are the currents coming out of the board, and these are the currents in the loops entering into the board. The wire is actually like this, like so. Solenoid इस तरह से दिखेगा. A wire wrapped over a cylindrical core इस तरह से. So when this wire is wrapped, when you connect these two ends of the wire to a cell or a battery, when you pass current, the current will follow a helical path. तो ये current का path बनाया गया है. It comes out, enters, 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 and so on. Let n be the number of turns per unit length. Per unit length. इसको मैं n by l लिख सकता हूँ. Where l is the length of the solenoid, length of solenoid l हो गया, and n is the total number of turns. ठीक है. n हो गया total turns, l हो गया length, then n by l gives the value of small n. This is number of turns per unit length. We wish to find magnetic field here. बाहर तो zero हो गया. We have discussed B out is zero. Suppose we wish to find magnetic field at this point. To find magnetic field at this point, we choose an Amperian loop in the form of a rectangle, like so. I will call this loop as A, B, P, C, D, Q. P and Q are those points where this rectangle just comes out of the or enters the uh, solenoid. Okay. Now, Amperian loop, for this Amperian loop, we'll use Ampere's circuital law, which we have discussed in the last class. What does this law suggest? That closed loop integral of Matic field along any closed loop is mu naught times current enclosed by a surface, open surface, enclosed by the loop. Now that open surface here will take in the form of flat surface only. So rectangular plate you can imagine, ये हमारा surface हो गया, उसका boundary हो गया ये, that is the loop. So we will start from our journey from A. So we'll move from A to B to C to D and back to A. एक complete loop करना है. At all these points, Matic field is uniform. Let this length be A be the length of the rectangle, and breadth be something like that. Now let me take it as L. We'll see afterwards. So integral B dot dl is mu naught times I enclosed. So this equation will become, now this integral will, this is for closed loop. So we will find this integral along each side of the rectangle. Let me rub these parts. So this is from A to B, this B to C, then C to D, then D to A. And that total will become mu naught times I enclosed. Let's see the integrals. First we see from A to B. A to B, the Matic field is along the axis. Any small element, dl vector, is also along the axis. So angle between B vector and dl vector from A to B is 0 degree. So B dot dl simply becomes B into this length. Integration dl means from A to B. From A to B, what is the length? This length I have taken as A. So I will write B into small a. If you wish, you can take as L also. Plus. So this part simply gives B times this length of the rectangle. Now B dot dl from B to C. B to C we will divide into two parts. I am explaining here. First we will move from B to P, and then we will move from P to C. P to C, all those points lie outside the solenoid. And we have discussed, students, that outside the solenoid, the Matic field is 0. If Matic field B becomes 0, then this integral will also become 0 from P to C. That is the reason. What about B to P? For points B to P, Matic field is not 0. Matic field is along the axis. But when we move from B to P, the dl vector will be directed perpendicular to Matic field vector. Since these two vectors are perpendicular to each other, their dot product will become how much? 0. Is it clear? So please convince yourself the explanation for these two reasons why B dot dl becomes 0. For B to P, reason is that Matic field is perpendicular to dl vector. B to P, in this region, magnetic field is perpendicular to dl vector. And P to C, here magnetic field itself is 0. That's why integral B dot dl is 0 from P to C, and that's why integral B dot dl is 0 from B to P. So both these integrals are 0. So 0 plus 0, total will become how much? 0. So this integral becomes 0. Now B dot dl from C to D, students, you can guess easily, all these points from C to D, they lie outside the solenoid. That's why B is 0, hence B dot dl will also become 0. Now whatever reasoning we have done from B to C, same will follow from D to A. The D to A will come in two steps. First will come from D to Q, then Q to A. D to Q, B is 0, and Q to A, magnetic field is perpendicular to DL vector. So B and DL vector, they are perpendicular. That's why for the path D to A, the total integral B dot DL also becomes 0. So out of these four paths forming a closed loop, only the path AB will contribute to the integral. और इसका contribution कितना हो गया? B times A. So plus 0 plus 0 plus 0 is equal to mu naught times. Now, what is I enclosed? See, current is running through the wire. ऐसा. So current is I, again it is I, again it is I. If you see carefully, here current is coming out. I, then I. In this figure, 3 times current is coming out. So current enclosed will become I plus I plus I, that is 3I. But that is just a representation of the figure. Actually, the length from A to B I have taken as small a. This length I have taken as small a. And number of turns per unit length I have taken as small n. तो total turns कितने हो जाएंगे यहाँ से यहाँ तक? Total turns हो जाएंगे small n into a. Clear? This is total number of turns inside this Amperian loop. एक टर्न में एक बार करंट बाहर को आता है. Number of turns है NA. So I. How many times I will come out? NA times. So I'll multiply this with I. So B dot DL is mu naught times I enclosed. I enclosed is the total current. अगर करंट एक से ज्यादा बार क्रॉस कर रहा है किसी सरफेस को, which surface? That surface which is enclosed by the Amperian loop. Then you have to add them. And if the currents are entering in opposite direction, so cancel भी कर सकते हैं. But because here all of them are dots, we will add them. So it becomes Na into I. This is total current enclosed. So बस simplify कर देंगे. A and A will cancel, and therefore the magnetic field for points inside this solenoid, it comes out to be mu naught times N times I. Note that N is not number of turns. I'm repeating again. It is a number of turns per unit length. Okay. So this is sufficient as far as the CBSE syllabus is concerned. क्या याद रखना है आपको? मैटिक फील्ड फॉर्मूला इज म्यू नॉट एन आई. बट डू नॉट फॉरगेट कि ये जो हमने डेरिवेशन किया है ये किस पॉइंट के लिए किया है. दिस पॉइंट इज वेल विद इन दिस सोलेनॉइड. सोलेनॉइड के काफी भीतर में, अंदर में, ऑलमोस्ट एट द सेंटर. इफ यू टेक दिस पॉइंट एट द पेरिफेरी, इसको दूर यदि एंड की ओर लेते हैं, देन वी विल नॉट हैव बी इज इक्वल टू म्यू नॉट एन आई एज द आंसर. इनफैक्ट किसी भी लॉन्ग सोलेनॉइड के एंड पर मैटिक फील्ड इसका आधा हो जाता है. दैट इज हाफ ऑफ mu naught times n times I. Okay, we will derive that afterwards. But before we derive them, let me now completely draw the magnetic field lines due to of long solenoid. We assume this to be a long solenoid. तो हमने देखा कि भीतर में, inside this solenoid, the magnetic field lines are parallel to the axis. And as you move at the end, it bends. वो bend करता है इस तरह से, just like bar magnet. Bar magnet magnetic field lines, if you remember, students, suppose these are the north and south poles of a bar magnet. So you draw the magnetic field lines like so. So if you see carefully, the pattern of magnetic field lines due to a current carrying solenoid is exactly similar to the pattern of magnetic field lines due to a bar magnet. We will try to observe this pattern of magnetic field lines with the help of our solenoid. So how will we observe the pattern? हम लोग क्या करेंगे, इस solenoid के अलग अलग हिस्से पर, ये हो गया सेंटर इसका, तो along the center, along its axis we'll put a magnetic compass. Magnetic compass कहाँ point करना चाहिए? Magnetic compass should point in the direction of magnetic field. Where is magnetic field pointing? Along the axis. इसका axis कहाँ है? सेंटर से एक लाइन परपेंडिकुलर इसके प्लेन का. प्लेन मीन्स प्लेन ऑफ द सर्कमफरेंस. सो दिस इज द एक्सिस. दिस विल बी द एक्सिस. इस तरह से एक्सिस होगा. So whenever you keep the compass inside this solenoid, the compass needle should point along the axis. इसको ऐसा रखेंगे तो compass needle इधर point करेगा, इधर करेंगे इधर करेगा. And if it is pointing in this direction, inside, outside it should point in opposite direction. मैंने कहा inside if it is pointing in this direction, outside it will point in opposite direction. क्योंकि ये finite solenoid है, that's why outside there will be magnetic field. यहाँ हमने B out 0 लिया था because that was a long solenoid. It is not a long solenoid. What would be more interesting? Inside मैंने कहा it will be along the axis. But as you come at the edge, आप अंदर से जैसे बाहर की ओर आते हैं, we should find that the magnetic field lines जो कंपास का needle है वो फिर इस तरह से घूमना चाहिए. Inside it is along the axis, outside it is oppositely directed, so it must take a turn जैसा कि हमने यहाँ represent किया है. So let us see whether we are able to see that turning of the magnetic compass using this particular solenoid or not. So let's check it out quickly. So students, as you can see, this is a circular coil or a solenoid. We will use the term solenoid if this is quite long. Long solenoid means its length should be quite large compared to its radius. Here we can observe the properties of solenoid. See, here there are 480 turns. Almost 500 turns have been wrapped around this particular cylindrical object, and it's hollow, you can see. Right now, if I put the compass wherever, anywhere, you can see the compass always points in that direction. You know, the compass is right now pointing in the direction of magnetic field of Earth. Now I will take this cell, I will pass current through this particular solenoid, and I will observe what happens to the compass, magnetic compass. First of all, I will keep the solenoid like so, and then I will try to bring the compass after passing current over here, and you should observe carefully the direction of magnetic field. So let me try if I could show it properly. So I'm connecting the ends of the wire to a 1.5 volt cell. Now the solenoid carries current. Now see the compass. The moment I bring it close to the solenoid, could you see it is pointing along the axis? And from here, if I turn this side, you can see it's turning. And here you can see it's exactly opposite to the direction of magnetic field which we expect inside. This is the direction of B in. I can't show inside also, but you should expect this to happen. It is along the axis, and outside it becomes opposite. Okay, this side also, let's go over to other side. Here it is pointing along the axis, and as you come this side, you can see how it's turning, clearly indicating the change in the direction of magnetic field. And here you can see it has changed the direction. Same thing we can expect here at the top. Now you see here, as I come a bit up, as I bring the compass a bit up, again it's pointing in the direction of magnetic field of the earth, clearly indicating that the magnetic field outside this solenoid is quite weak. Only when you put the compass very close to the solenoid, the compass is pointing in required direction. The moment you take it far from the solenoid, it starts pointing in the direction of magnetic field of earth. The magnetic field of earth dominates. Now let me invert it and try to show you. From close. See, inside I was willing to show you. You can see inside the magnetic field is along the axis. It will turn this side, then it will turn that side, like so. And let's see upward. Could you see it's turning here also? This side, very good, excellent. And at the bottom part, let me try to show you. See the concentrate on the needle. Yes, it's changing the direction. I think this is sufficient, students. This gives you an idea regarding the direction of the pattern of Matic field lines due to a solenoid. Okay, students, having seen the pattern of Matic field lines due to a solenoid, we can now understand that the pattern of Matic field lines due to a current carrying solenoid is exactly similar to that of a bar magnet. So what we have discussed today in the derivation, that at the center of a long solenoid, what do I mean by long solenoid? Long solenoid means the length of the solenoid is quite large compared to the radius of the solenoid. That's the meaning. So in case of a long solenoid, near its center, the magnetic field we have discussed is given by what formula? B equals to mu naught n times I, where n is the number of turns per unit length. I is the current flowing through the solenoid. So this is the formula we discussed. Now remember, this is the formula for magnetic field near center. In fact, at center of a long solenoid. When I'm stressing on this particular fact, that means the value of magnetic field as you move away from the center towards the end of the solenoid will change. It is strongest in the middle, it will decrease, but then how much? So at the ends, at end, at an end of a solenoid, of a long solenoid, the value of magnetic field B is half of this value, half mu naught Ni. This we will be able to do it, understand it, provided we discuss first a finite solenoid and derive the expression for magnetic field on its axis using Biot-Savart law. The basics for all of these discussions which we are doing is, remember students, the Biot-Savart law. We have used Biot-Savart law for finding the magnetic field due to a circular coil. That formula we will use for finding the magnetic field at points on the axis of a solenoid. But that I'll take up in some later class. I'm willing now to discuss without using that rigorous mathematical formula why this magnetic field should be half of the magnetic field at the center. What I'm going to discuss now, students, is very important, very interesting also, and it will help you in arriving this particular result without any mathematical rigorous treatment. And what I'm going to discuss, that is actually inspired from one of the discussions in a famous book of physics by Richard P. Feynman on the concept of symmetry. Although it was not in this particular context, but remember students, whatever concept we discuss in one particular context may sometimes be applicable to other context. I feel restless to give that particular treatment. So that was given by R.P. Feynman. So what I'm going to discuss is based upon his idea of symmetry of solving some of the problems. In his famous series of lectures, so lectures in physics, there are 3 volumes, volume 1, 2, and 3 by Richard P. Feynman, Nobel laureate in physics. So he argued about the concept of symmetry in a particular problem. Similar to that analogy, I will discuss this particular thing. Given that magnetic field at the center is mu naught Ni, let us discuss by symmetry why it should be half of mu naught Ni at the end. This magnetic field is known at the center. This point I'll call it as O. So magnetic field at the center is how much? Mu naught times N times I. I will divide this solenoid into 2 parts. From the middle, I'll divide it into 2 halves. Now, since it is infinitely long, dividing it into 2 halves, the each part or each half that you get is also infinitely long. Infinity by 2 is infinity. After dividing into 2 halves, the pattern that we will get, the parts that we will get, I'm drawing them again. So this is one part. This will continue like so, and the other part will be something like this. So what we have done, at the center we know the value of magnetic field. So this will continue like this. So this is also infinitely long, this is also infinitely long. These two are the halves of this particular long solenoid. So this point was the O, point O. At this point O, the total magnetic field BO, we have discussed it is mu naught times N times I. This left half I'll call it as 1, the right half I'll call it as 2. Now the point O, which was at the middle, at the center of this long solenoid, now it becomes a point at the end of this solenoid. इसके भी एंड पर हो गया ये और इसके भी एंड पर भी हो गया, like so. If you concentrate on this solenoid, ये इसके right end पर है, for this solenoid ये इसके left end पर है. But since the direction of current determines the direction of magnetic field, direction of current is like so. So in both the cases, magnetic field will be in same direction. So let the magnetic field at end O of left solenoid be B1. Let the magnetic field at the end O of right solenoid be B2. Symmetry कहता है, by symmetry B1 must be equal to B2. There is no justification for awarding more magnetic field to B1 than B2. There was a long solenoid, center पर magnetic field B है, center से मैंने इसको दो हाफ में डिवाइड कर दिया. Both these halves are exactly identical. Same current है, same number of turns per unit length, एक ही material है, वगैरह वगैरह. Because they have similar parameters, therefore the magnetic field at the ends must be same. So B1 must be equal to B2, but the total magnetic field at point O is B1 plus B2. B1 इसके कारण, B2 इसके कारण, and this total is known to us as B is equal to mu naught and I. If they are equal, let each one of them equal to x. Then we will get x plus x is equal to this much. 2x is equal to this much. So x will be half of mu naught and I. Therefore, B1 is equal to B2 is equal to half of mu naught and I. Is it clear, students? That was an excellent argument given in the book which I have described. So I was highly influenced by this particular derivation because here, just by invoking the concept of symmetry without any mathematics, just by invoking the concept of symmetry in physics, we have been able to solve for magnetic field at the end. But then, if you ask me to find the magnetic field at this point, we cannot use this particular concept. Then we'll have to go through that rigorous mathematical derivation. So, having understood the solenoid, the last topic that I would like to discuss today is a toroid. So if you have a solenoid and if you hold that long solenoid and you turn it, bring the ends of the solenoid together. Suppose you have a finite solenoid, ends you bring it together, then these two ends you hold and put them together in the form of a circle. The pattern which you will get is called as toroid. So it's not very difficult, so let me discuss it quickly. So it looks something like this. So it doesn't have an end because it forms circular structure. The dashed part is on the other side of the board and the solid part is on this side of the board. Suppose current I is flowing through this particular wire. Now here it suppose enters, here it comes out, or here it enters, comes out. So one of the places you have to assign a dot. So it is entering here, coming out here. This is dot, these are dots. These dots I am indicating for current. Dot means it is coming out of the plane of board. At the other ends of the wire, there the current will enter. It is coming out and it will enter also. It is entering at these regions, suppose. Yes. So inside it is cross. And likewise everywhere. Now we wish to find suppose magnetic field here in this region, outside here, and in between the toroid. So I'll choose suppose this point as A, this point as B, and this point as C. Let us first try to find the magnetic field at A. So we will use Ampere Circuital Law and the concept of symmetry. Through A, we will draw, this is the center of the toroid. Through A, we will draw an Amperian loop like so. Symmetry says at all the points, so we will invoke again symmetry. First, we are discussing for point A. Symmetry says at all points on this Amperian loop. What is this? So this is our Amperian loop. At all the points on this Amperian loop, the magnetic field must be tangential and it must have same value. It must be tangential along the tangent and it must have same value. So applying, so those two statements you should write yourself: tangential value of magnetic field and tangential direction of magnetic field, and it has same value. Ampere Circuital Law says integral B dot dl is mu naught times I enclosed. Now, inside this Amperian loop, do you think there is any current? The current is entering here, coming out here, entering here, coming out. In this particular wire, current is running. So there is no amount of current entering or leaving the flat surface. Suppose you take this flat surface being enclosed by this loop. There is no current entering or leaving this flat surface. Therefore, I enclosed becomes how much? 0. And that's why magnetic field will also become 0 for points which lie completely inside the toroid. So magnetic field at point A will become 0. Next, the same thing we will discuss for point B. For point B, same argument will be there based on symmetry, the magnetic fields at all the points on the Amperian loop. Now at point B, the Amperian loop will be like so. Here we will draw an Amperian loop. It will lie midway between the ends of the toroid, like so. This is a circle. And let us assume that flat surface with this perimeter as the surface enclosed by this loop. So integral B dot dl is mu naught times I enclosed. So B dot dl becomes B into this length. Because B is tangential, B and dl will be in same direction. So it becomes B times dl times cos 0. Cos 0 will be 1. So what will be this length? This length will be 2 pi r, where r is the radius of this Amperian loop. From the center to this point on the Amperian loop, I call this distance as r, radius, is equal to mu naught times. Now I enclosed. Inside this Amperian loop, we have to observe. Inside this Amperian loop, the current is only entering all these crosses. Here also you can draw the crosses. So cross, cross, cross everywhere. So all these currents which I have represented by cross, here, they are entering into the flat surface which is enclosed by this Amperian loop. So we have to write in place of I enclosed the total amount of current. I plus I plus I. Now how many times will current enter? The number of times current enters is equal to the number of turns in the toroid. So let n be the number of turns in the toroid. Turns number. If capital N be the number of turns, and in each turn the current is I, so I enclosed will be n times I. So B will become how much? B will be mu naught n I upon 2 pi r. So this is the formula for magnetic field for points like point B. Then at last we are left with point C. Point C lies completely outside this particular toroid. For point C also we shall use similar concept. First of all, we have to make an Amperian loop. So Amperian loop will be a circle like so, and let this distance be r dash. Then we have integral b dot dl equals to mu naught times I enclosed. Same concept. Now what is I enclosed? Now you might feel that there are entire toroid itself is inside this Amperian loop. Each turn has current I. Number of turns is capital N. So therefore total current should be Ni. Be careful, but we have discussed that this Amperian loop is to be associated with some surface. The surface I choose as this flat surface. This one. The flat surface lies on the plane of board. So this is the surface enclosed by this particular Amperian loop. Okay. Now inside this we have dots also, we have crosses also. Dots cross, dot cross, dot cross. That means current is entering at some locations and current is coming out of the flat surface at some locations. And the number of dots is equal to the number of crosses. So the number of times current enters the number of times current enters into the flat surface is equal to the number of times current leaves the flat surface. And therefore the total current enclosed will be as many times current enters, as many times current leaves. So as many plus i's, as many minus i's. So the total becomes 0. I hope you can write the reasoning on your own part. Please try to write yourself. So since the current enters as many times the flat surface enclosed by this loop, as is the number of times current leaves the surface, therefore the total current enclosed will be how much? 0. And if this becomes 0, B also becomes 0. So what we discussed, that if this is the toroid, then at these locations magnetic field is 0. Completely inside also magnetic field is 0. Only in this portion there is some magnetic field, and that magnetic field is given by the formula mu naught times n by 2 pi distance of this point from the center times I. This one, which I have discussed earlier. So this is all about solenoid and toroid. Hope the concepts which I tried to convey to you are clear to you. You could understand them properly. Please try to make the notes on yourself, students, by yourself. And if in case if you have some queries, please try to put them in the query link given in the school's website. So I wish you all the very best. Read well. Take care. See you in the next class. Thank you.